Welcome everyone. In this video, we'll master a popular interview problem called container with most water. We'll go step by step and then write an optimized JavaScript solution using a powerful concept called the two-pointer technique. By the end of this session, you'll understand how to visualize the problem, improve from brute force to a linear solution, and why this pattern is so useful in coding interviews. Let's first understand what the problem is asking for in simple terms. You are given an array where each element represents the height of a vertical line drawn on an x-axis. Your goal is to find two lines that, together with the x-axis, can hold the maximum amount of water. Here's an example. Imagine an array with the numbers 1, 8, 6, 2, 5, 4, 8, 3, and 7. The correct answer is 49. That's because the two tallest lines, one with height 8 and another with height 7, form the container that can store the most water. And here's the key insight: the water area between any two lines depends on two things. First, the shorter line's height, and second, the distance between those two lines. The wider the gap and the taller the shorter line, the more water the container can hold. This isn't just a math puzzle, it's a favorite question in big tech interviews. It tests how well you think logically and how efficiently you can optimize a solution. By learning it, you'll understand one of the most powerful algorithm patterns, the two-pointer technique, which appears in many other problems too. Here's a little insight to remember: sometimes, the best way to find more water is to move the shorter line. That's the secret behind the optimized solution we'll build. Let's begin with the basic approach, called the brute force method. Here, we calculate the water area between every possible pair of lines. The formula goes like this: take the smaller height of the two lines, and multiply that by the distance between their positions. That gives the area of water those two lines can hold. We repeat this for every pair of lines, and keep track of the maximum area found so far. While this method works, it's very inefficient. The time complexity is O of n squared, meaning, for every line, we compare it with all lines after it. That's too slow for large arrays and wastes time checking pairs that clearly can't be the best. So yes, it's correct but far from optimal. Now, here's the clever optimization, the two-pointer technique. Instead of checking every pair, we start with 2 pointers, one at the beginning of the array and one at the end. These two form the widest possible container. We calculate the area between them the same way: take the shorter height and multiply it by the distance between the pointers. Then we ask, which line limits the height? It's the shorter one. So, we move the pointer pointing to that shorter line inward, hoping to find a taller line that might increase the area. We keep doing this, calculate the area, compare with the maximum, and move the shorter pointer, until both pointers meet in the middle. This approach reduces the time complexity from O of n squared to just O of n, a huge improvement. Now, here's the clever optimization, the two-pointer technique. Instead of checking every pair, we start with 2 pointers, one at the beginning of the array and one at the end. These two form the widest possible container. We calculate the area between them the same way: take the shorter height and multiply it by the distance between the pointers. Then we ask, which line limits the height? It's the shorter one. So, we move the pointer pointing to that shorter line inward, hoping to find a taller line that might increase the area. We keep doing this, calculate the area, compare with the maximum, and move the shorter pointer, until both pointers meet in the middle. This approach reduces the time complexity from O of n squared to just O of n, a huge improvement. Now that we've seen the code, let's slow down and really understand what's happening behind it. We'll break the logic into two parts, the setup and the loop process. First, the setup, we begin by placing two markers, called pointers. One pointer starts at the very beginning, that's the left pointer, and the other starts at the very end, that's the right pointer. So we're starting with the widest possible container, the full width of the array. We also create a variable called maxWater and set it to 0. That's where we'll keep track of the biggest water area we find. Now, the loop process, while the left pointer is still to the left of the right one, we keep doing 4 simple steps. Calculate the width. That's just the distance between the two pointers. For example, if left is at index 1 and right is at index 8, then the width is 8 minus 1, which equals 7. Calculate the area. We look at the heights of the two lines. The smaller one limits how much water we can hold. So the area is the smaller height multiplied by that width. Compare and store the maximum. If this new area is bigger than what we found before, we update our maxWater variable. Move one pointer. But here's the trick, we only move the pointer that's at the shorter line. Because moving the taller one won't help, it can only make the width smaller without increasing the height. We keep repeating these steps until both pointers meet. And that's when we've checked all meaningful possibilities, efficiently, in just one pass through the array. So think of it like this, you're standing between two walls trying to trap rainwater. Each time you move, you either find a taller wall or lose width. The key is finding that perfect balance between height and distance, and that's exactly what this algorithm does. Let's make this even easier to understand with a real example. Imagine the array has the numbers 1, 8, 6, 2, 5, 4, 8, 3, and 7. Let's go step by step. Step 1, starting state, our left pointer is at the first number, which has height 1. Our right pointer is at the last number, which has height 7. The distance between them is 8 positions. The smaller height is 1, so the area equals 1 multiplied by 8, which gives us 8. Now, we move the left pointer inward, because that's the shorter one and limits the container's height. Step 2, left pointer moves one step right, now the left pointer is at height 8, and the right pointer is still at height 7. The distance between them is 7 positions. The smaller height is 7, so the area is 7 multiplied by 7, which gives us 49. That's our new maximum area. Step 3, move the right pointer. We move the right pointer inward, because height 7 is shorter than 8. Now the right pointer is at height 3. We calculate again, the smaller height is 3, the distance is 6, so the area is 18. That's smaller than 49, so maxWater stays the same. We keep repeating this process, move the shorter line, calculate the new area, compare it with the maximum. Each time, we get smaller widths but sometimes taller heights. Eventually, both pointers meet, and the largest area we found remains 49. So, the answer to this example is 49 units of water. You can imagine this visually as two tall walls, one slightly shorter than the other, and a wide base between them holding a huge pool of water. That's the container with most water our code is finding. Now let's wrap up with what we've learned, and why this problem is so valuable. First takeaway, the two-pointer technique is pure magic. It turns what looks like a complex O of n squared problem into a fast, simple O of n solution. Instead of checking every combination, we intelligently narrow down the possibilities. Second takeaway, always remember, the shorter line limits the container's height. By moving it inward, you give yourself a chance to find a taller wall and possibly a bigger area. Third takeaway, we used only a few variables, left, right, and maxWater, which means the space complexity is constant, O of 1. That's as efficient as it gets. And here's a bonus insight, optimization isn't about doing more work, it's about doing only the right work. this problem teaches exactly that mindset. Now that you understand how the two-pointer approach works, you can apply the same thinking to many other problems, like trapping rainwater, max area of island, or even container with K-lines. Each of these builds on the exact foundation you learned today. So congratulations, you've not only solved this problem, you've unlocked a whole family of algorithmic patterns. Keep practicing, and soon you'll see two-pointers everywhere.